Okay, very good afternoon, all the participants. I am Vaibhav Garg. I am faculty in Water Resources Department of Indian Institute of Remote Sensing, Dehradun. Today, in this session, I am going to cover snow and glacier mapping and associated hazards and with main emphasis on avalanche vulnerability analysis. So this is how the snow looks to us in the field. So what is the difference between snow, ice and glacier? So all of you know that snow, it is a porous and permeable aggregate of ice crystals, and these ice crystals are interconnected by air and water, and generally the density is less than 400 kg per cubic meter. So if you see the difference between snow and ice is the when the interconnecting air and water passage between the ice and crystals are sealed off. The process is known as pore close off. Then the ice are formed. So generally the density of ice is it varies between the 830 to 923 kg per cubic meter. So if you see the glacier, when ice mass became sufficiently large and then due to gravity and creeps start moving, then glaciers are formed. So our ice should be formed due to metamorphism and recrystallization of naturally fallen snow on the land surface of earth. So glaciers would have ice, snow, water and all debris as well. So you can see here we differentiate between the snow and ice based on the density. Now you can see here there are different type of snow and ice. So freshly fallen snow, it will have the density in the range of 50 to 70 kg per meter cube, whereas your damp new snow will have 100 to 200 kg per meter cube, settled snow 200 to 300 kg meter cube. So if you see the fern, it is 400 to 830, and if you see glacier ice, it has the density of 830 to 923 kg per meter cube. So based on the compaction and the density, we can separate out the snow and ice. So in the initial slides, we will focus on the snow. So snowpack characterization. In the snowpack characterization, we can study the changes in the snow grain size, liquid water content. These are the important parameters. Those are helpful in the avalanche forecast. Along with this grain size, albedo is also an important parameter to assess the snowpack stratigraphy and the avalanche. So if there is a sudden change in the albedo during the winter, can cause formation of ice layers, and fresh snow whenever falls over it, it may cause the avalanche. So whereas broadband albedo, it is important parameter for runoff modeling and the energy balance studies. So you might have studied there are different type of snow melt runoff models. So in those models, there are temperature index based models. Some of them are energy balance based models, where we study the net radiation, how much it is coming, how much is going back, and how much energy left on the surface, which can help to melt the snow. For that purpose, we require this broadband albedo in these kind of studies. So for snow, we can use both optical data and the SAR data, or especially in the microwave data, the SAR data. So it depends upon your objective. See what kind of snow cover map you want to generate. If you want to generate a snow cover for the larger region, then you can go for the medium resolution sensors such as AWAVS. And if you want to do the snow cover mapping of a specified area, then you can go for a higher spatial resolution like LIS3 and the LIS4. So I will touch upon some of the slides how snow appears in different spatial resolution data, optical data sets. So here you can see here, if you have some knowledge of remote sensing, you know that the features present on the surface of the earth can be discriminated based on their spectral signature. So all of you know that these are the spectral response. This is the spectral response of the snow, and you can see here in the visible region it reflects highest and as compared to the other features present on the surface of the earth. You can see how distinct it is. So based on these spectral signatures, we can identify the snow or any other feature present on the surface of the earth. So you can see here, if it is a snow, this is the spectral response of the snow, this is the spectral response of the ice, and this is the, if there is a contamination of the snow, fresh snow, then the response will change and it will be like this. So this is how the snow fed region in the AVS sensor it will looks like, or it will appear. This is the example of band 2, which is the green band. You can see here the snow, it reflects highest, as we have seen earlier in the spectral response curve. So we have brighter, more brighter pixels wherever we have snow. But if you see this sphere band, you can see here it is totally opposite what we have noticed in the band 2, that is a green band. If you see the band 5 sphere band, we have noticed that in the sphere region, whatever energy incident upon the snow, it gets absorbed by the snow. So that is why if you see here in this sphere band, you can see that whatever energy incident upon the snow, it get absorbed. Because of that, it appears darker in the color. So using this kind of techniques, we can identify snow in the remote sensing data. So this is how the false color composite of this 56 meter AVS data will looks like, and you can visually analyze where is the snow, where is the vegetation, and other land features. Similarly, if you see the band 2 of list 3, so you can see here again, you can see some bright pixels of snow. And now you can see, if I take the band 5, that is sphere band, then again you can see that there is a absorption of the energy, and we cannot there are less bright pixels here in this image. So this is the false color composite, and we can see where is the snow in the satellite image. Similarly, you can see in the Landsat OLI image, Landsat 8 OLI sensor, 30 meters data. These are the different bands, blue, green, red, and you can see again the sphere 1, sphere 2, how the snow will appear in these bands. So you can see based on the spectral signature in different wavelength region, we can identify the snow, and we can map the snow using the remote sensing data. So this is the false color composite of the Landsat data set. And then now you can see snow also appears white in color in the satellite image if you are talking about the FCC, and similarly cloud will also appear bright or white in color. So how should I differentiate between whether it is a snow or it is a cloud? So I need the multispectral remote sensing data. So you can see here using this spectral signature, if you see that this is the spectral response of the snow and this is the spectral response of the cloud. So we have seen that in the visible region, snow reflects highest, even the cloud also reflects highest, but in the NIR region, region beyond NIR, snow absorbs all the energy incident upon it, and whereas cloud, it still reflects some energy back to the sensor. So using this sphere band, we can separate out the snow and cloud from the optical remote sensing data. If we take these two bands in the feature space, you can see that we can easily separate out the cloud pixels in the image very easily. Now you can see here, if I have a Landsat data, if I generate the standard false color composite, I am not able to discriminate between the snow and the cloud present in the image. Now if I bring the sphere band into consideration and I generate the false color composite, it will looks like this. So still I can see that these pixels are snow pixels, but there are some pixels of cloud. If I bring the sphere 2 in the analysis, you can see here, and again I generate the false color composite, I can see that these are the snow pixels, and there are some cloud pixels present in the image as well. So using the sphere band, we can separate the snow and the cloud. So whenever we do the snow cover mapping, we should be very critical and we should see whether the cloud is present. If cloud is present, we should eliminate that from the analysis. So for we have seen that visually we can identify snow is present in the image. Then how to extract the snow from the satellite image, that is optical remote sensing data? We can use simple band ratioing technique where we use two different bands, green and sphere. If we take the normalized difference of the green and SWIR band, which we called as normalized difference snow index or NDSI, we can extract the snow from the optical remote sensing data. So we have, why we are using green and SWIR, we have noticed in the earlier slides that in the green region the snow reflects highest, and in the SWIR region snow reflects less as compared to green, and it is much less, and the cloud has more reflectance in SWIR as well. So we are able to discriminate cloud and snow in these two bands. So we have used these two bands for mapping the snow from the optical remote sensing data. So this is one of the typical optical remote sensing data of Sentinel-2 MSI sensor, and if I apply this band ratioing technique, I could generate this kind of output. So this is the binary output where the bright pixels are snow and the dark pixels are some other land feature. So if I know the number of pixels, if I multiply that with the grid size or the resolution of the sensor, I can get the total area of the snow present in the image. So using this approach, the different snow cover areas products are available. So most widely used is the MODIS snow cover product, that is mod 10 A1 or mod 10 A2. These are of different spatial resolution and different products. So this is daily snow cover product. This is 8-day composite snow cover product. So in daily we will have more, all of you know that the snow falls in the higher altitudes where we may have the cloud present in the image. So in the daily we will have more clouds. In 8-day composite the frequency of cloud may reduce. So most widely we have is the 8-day composite snow product has been used for the snow cover mapping from the MODIS data set. So similarly we have used this data and we could generate the long-term snow cover map of entire northwestern Himalayan region, and which covers these 3 states, 2 states and 2 UT now. So Uttarakhand, Himachal Pradesh, and the UT of Jammu and UT of Ladakh. Using this MODIS data, we have generated this long-term snow cover map of this area. So in this, both the sensor Terra and Aqua sensor data has been used, and then in this analysis we have used different cloud removal approaches. First is we have used the elevation mask. At a certain elevation only there will be snowfall, so that we have used in this analysis. We have used that if there is a snow in the previous wherever cloud is there, we have used the approach where if there is a cloud, if there is a snow before the date of the image and after the date of the image, then we have interpolated and we have improved the snow cover mapping in this kind of analysis. And when we have done this kind of long-term snow cover mapping, we have also analyzed the snow persistence. So this is the annual snow persistent across entire high mountain Asia. You can see here some of the area the snow is persistent, and where some region the snow is not persistent. So the snow cover is reducing in some of the area in this region. So we have done the snow cover mapping, but for the hydrological studies or the disaster related to snow and glacier, is it the snow cover area estimation is enough? So I don't think so that only the snow cover area is important. We required some of the snow physical parameter properties such as the wetness, density, and the grain size, which may be required by hydrological models for the snow melt runoff and the avalanche. We can improve the avalanche modeling if we have these snow physical properties available with us. So for these snow physical parameter retrieval, we require microwave data, and specifically we use the synthetic aperture radar data. All of you know that synthetic aperture radar data is active microwave data, and because why we are using active microwave data, because of its advantages such as the spatial resolution. So it is the spatial resolution of the SAR data is much better than the passive microwave data. So this is how the snow fed region will appear in the SAR data sets. So you can see here, this is the Gangotri glacier. It is in optical how it appears, and in the SAR how it appears. This is the Samudra Tapu glacier region, how it appears in the reset 1 SAR data sets. So you can see here, if it is a snow present in the if it is a dry snow present in the image, due to the penetration in the snow, we will get less energy back to the sensor. So this the snow fed region will appear darker in the SAR images. So there are different SAR sensors available. Some of the past data, it is available at present. Sentinel 1A, 1B, I think only 1B is available now. Then ALOS 2 is available, then Reset 2 is available. So these sensors work in different frequency, and they have different penetration in the snow and the glacier regions. So in the active microwave remote sensing data, active microwave remote sensing data, we analyze the backscatter. So how much is the backscatter? So from the snow surface, we will have the backscatter back on the sensor. It will be the sum of the backscatter from the snow surface, volumetric scattering, and the scattering. If it is a shallow snow pack, then we may get some backscatter back from the ground as well. And if there is a vegetation present in the surface, then that will also reflect back, and we will have some backscatter back to the sensor. So it depends upon the condition of the snowpack. This total backscatter what we are receiving at the sensor may change. So this depends upon the volumetric liquid water content of the snowpack, snow layer thickness, snow roughness, snow grain size and shape, snow layer temperature, and snow layer density profile. So these parameters also affect the backscatter of the snow. So I will show you, if it is a dry snow, means the liquid content is less. So we will have only the volumetric. We will get the backscatter from the volumetric scattering, and the scattering from the surface below the snowpack. So this much we will receive back into the sensor. If it is a wet snow means some water is present in the some wetness is present in the snowpack. So what will happen? It may not be able to penetrate. So due to the low penetration, what will happen? We will get back the backscatter from the surface and the volume scattering, and we will get the sum of these two as backscatter at the sensor. So here I have shown that the incidence angle. Also, all of you know that the SAR sensors are side-looking sensors. So if this incidence angle of the sensor also playing critical role in the backscattering. So you can see here how the backscatter changes from the snow surface with the change in the incidence angle. So if we go for higher incidence angle, we will get less backscatter. Similarly, if wetness increases, you can see here with the increase in the wetness, the backscatter decreases. So similarly, I have depicted here in this figure that if it is mostly if there is a less wetness or liquid water content in the snowpack, so this will be the condition. So it is a condition of January in the Gangotri region. So we are getting more bright pixels in the SAR image. It is a composite of VV and VH, two different polarization. And then here you can see here this is the Bias region of March, when there is a wetness the snow is wet, and you can see here that we have more dark pixels in the analysis. So this is the reason why we are getting less backscatter and more backscatter in this time conditions. So if we have the SAR data, we can process it. And first, all of you know that these are the data, the SAR data. It is available in slant range and azimuth range. Then we have to do the multi-looking. Then we have to create a creation of multi-look power image. And then with the help of external DM, we can geocode this data. And then based on this, we can also identify the layer, shadow, and foreshortening. I will let you know what is all these. the problems associated with the SAR data, and then we can generate a backscatter image. If we have these information available with us, we can using the inversion models, we can identify the snow cover area with emphasis on wet snow and dry snow using this kind of approach. So this is the this is the your surface. All of you know that snow falls in the higher altitudes, so we have this kind of topography, and these sensors, SAR sensors, are side looking sensors. So if this is the topography and your sensor is looking like this, so you may have the issue of foreshortening. Means this if you see the in the on the ground, both of them are of same size, these slopes, but because of foreshortening we are getting less area here and more surface here in the due to this foreshortening issues. And then you can see here you may have the shadow problem as well. Your if your topography is like this, your sensor is looking like this, then this region will be under shadow. And then layover, so you can see here this is your surface and your sensor is looking like this. So you can see here this part will appear before this the part which is on the ground. So this is called as layover. So these kind of issues you may face in the SAR data, and these effects may change with the local incidence angle. So once you have the raw data, you have to do the multi-looking, then you have to geocode data. Why geocoding is required? So that we can overlay our boundaries and we can do the analysis. So I told you that layover, shadow, they will change with the incidence angle. So you can see here, if I use the low incidence angle, you can see that most of the area is going into the layover and shadow. And if I use high incidence angle data, you can see here I am getting less layover and shadow issues in the data. So while doing the analysis, I should choose the data accordingly, what kind of analysis I want to perform and what kind of data I have. So it is always preferable that we should go for higher incidence angle data for snow cover mapping. So this is how the snow cover area will look like in the SAR data. This is the Gangotri region. You can see that this is the Gangotri glacier, this is Satoban glacier. And as I told you that snow we can get very less energy back to the sensor because this is at this time the snow will be wet. So because of the wetness we are getting less energy back to the sensor. So because of that they appear dark in the SAR data set. So these are the this is how the snow area appears in the SAR data sets. So how to interpret the SAR data? You can see here there is a sudden change in the backscatter. So this is one of the bridge present here. Here you can see here this is some smooth area. So this is the snow cover area. This is the shadow region. This is the layover. So you can see here how layover will appear in the SAR data. So this is bright pixels are the layover. And then you can see this is the forest patch. So you can see a zoomed version of this. This is the forest patch. This is layover. This is shadow. This is snow cover, and this is the bridge present in this region. If you see, this is the optical data or Google image. You can see here this is the snow observatory of DGRE in Dundi, Manali. On same you can see here because this is a structure. You can see here this appears bright in this image. And this is the snow observatory of DGRE present in the image. So this is how we can interpret the SAR data. And so using this the dielectric constant and the condition of the snow, we can map the snow wetness. So you can see here we have used different approaches to map the wetness, the snow, that dry snow, wet snow. So we have used this the ratio technique. So here we have taken the ratio of the backscatter image of the non-snow time and the winter time snow image. So this ratio we have generated, and you can see here because of this the low values they represent the the wet snow. Okay, so these you can see here wherever we have this low value of the ratio, we have this wet snow present in the image. So this is how we have done the snow wetness mapping. And as I told you, there is a relationship between the dielectric constant and the density and the wetness. So if we have if we can estimate the dielectric constant, which we can do using the remote sensing data, that is SAR, active remote sensing data, active microwave remote sensing data, SAR data, we can correlate that dielectric constant with the wetness and the density, and we can generate this kind of snow density map and the snow wetness map. So using the inversion models, we can generate snow density and snow wetness map of any region if we have the synthetic aperture radar data. So we can also validate our results. We have the DGRE. They have their stations in Dundi, Solang, and Palchang. So from there we have received the data of the density and wetness, and we have compared that, and we have achieved very good result between the derived wetness and density snow density maps. So you can see here even we have used the optical remote sensing data. How much is the snow cover retrieved using the optical remote sensing data, and how much snow cover has been retrieved using the SAR data. So there is a good comparison between the optical and SAR data. So whenever we have cloud present in the optical data, we can improve our snow cover analysis using the SAR data sets. So this is the condition of dry snow and wet snow, how much match we have achieved. So this kind of analysis we have done, and I have taken this analysis, or we have published this analysis in the this particular reference. You can follow this reference, and you can further study on the estimation of snow and the snow cover area, and wet snow cover area, and dry snow cover area. So using the reset data, reset 1 data, the ISRO's reset 1 data, we have also done some similar kind of studies for different river basins in India. So this is the sample MRS reset 1 MRS data of different dates of different region, Gangotri area, and this is the Manali area, and you can see here this is the snow cover area retrieved using the reset 1 MRS data. Then we have improved our snow cover estimation by incorporating SAR data, the digital elevation model, and optical data, and these are our results of snow cover mapping. So this is how the snow cover mapping has been done. So here then once we have done the snow cover mapping, we have differentiated between the dry and the wet snow. So you can see here some part there is a wet snow present in the area, and most of the area it is dry snow. So this kind of analysis we can do. Now why I'm talking about the dry snow, wet snow. So if you have heard that this year in Uttarakhand we have numerous avalanches. So why this happened this year, I have shown you this here in this image. You can see here this was the condition in the April 2021, 11th April 2021. This is the Sentinel-2 image, optical image, and you can see the same date, 11th April 2022. You can see here because of the increase in the temperature, there is a sudden increase in the temperature this year in the from the mid-March. You can see here in the March onwards, 18 to 14 month onwards, the temperature was high as compared to previous years. So the melting started early in this year. So what has happened then, due to the melting, the snow has become wet. The liquid water content has increased, and because of the fresh snow fall over this wet snow, it will result in the avalanche. So that is why we have faced so many avalanche this year in this region. So this is I will show you some case studies how we can analyze the probable or vulnerable snow avalanche areas using remote sensing data, and the using modeling approaches. So what is avalanche? An avalanche is also called as snow slide or a snow slip. It is a rapid flow of snow down a sloping surface. So these avalanches are typically triggered in a starting zone from a mechanical failure in the snowpack. So this kind of avalanche is called as slab avalanche, when the forces on the snow exceed its strength, but sometimes only the gradually widening loose snow avalanche. So after initiation, avalanches usually accelerate rapidly and grow in mass and volume as they entertain more snow. So if the avalanche moves fast enough, some of the snow may mix with the air, forming a powder snow avalanche. So there is a slabs avalanche, loose snow avalanche, and then there is a powder snow avalanche. So I have shown you some of the photographs of different type of avalanches. So you can see here, and then due to avalanches, you can see here how many people have been affected in a year in different regions. You can see here due to these kind of avalanches, these many people have been affected. And if you see the how many people got or there were deaths in these regions. If you see in India, in 2005 there were around 250 people died due to avalanche. In 1995 again 250. In 1988 around 250. So you can see here the avalanche causes huge damage to both human and the property. So we have done the susceptibility to snow avalanche. We have done one analysis using the AHP approach, analytical hierarchy approach. So in this, what we have done, we have used different parameters. We have taken only the static parameters, slope, aspect, curvature, elevation, and we have done the potential avalanche formation zone mapping. It has been done. So these are the layers: elevation, slope, aspect, curvature, and the land use, land cover. So from this we have categorized them in different classes, and then we have given certain rating based on their importance or influence over the avalanche, snow avalanche. And then you can see here, this is the land use, land cover map, this is the slope map, this is the elevation map, this is the aspect, this is the curvature. And then we have provided different weightages, and then we could generate this kind of potential avalanche formation map. So you can see here the regions in the red color, though these regions are highly vulnerable to the snow avalanches based on the snow. And this is the this study we have done for the Alaknanda river basin. So you know that there are different pilgrimage sites such as Badrinath, Kedarnath. So these are there present in this region. So and most of the people find these kind of issues in this region. So we have identified these areas, and then if the avalanche take place, how much road will get affected due to the avalanche. That kind of analysis has been done. And then if the avalanches occurs, what will be its formation, how much area it will cover. So that analysis has also been done. So this is based on this analysis, we have found that which stretch of the river of the road is vulnerable to the or susceptible to the avalanche. Those kind of analysis we could do it, and this has been published in this ISRS publication. So this is how we can study, or we can do the vulnerability analysis for the avalanche, snow avalanche. We can use the modeling approach. Here we require the model. So in this study has been done by one of the student. So in this study he has used this he has studied the upper Bias River basin, where we have the observatory from the Dundi, Solang and Manali by the DGRE, and these are the different altitudes of these observatories. So in this study, the following methodology has been adopted, where they have used the RAMS model. So RAMS is the Rapid Mass Movements Simulation model. So it is a commercial model. So you have to provide the different snow parameters, images. In the from the satellite image, you can drive these parameters, and you can force this model, and you can do the analysis, and you can analyze the snow avalanche. So this is he has done the study for different sites. These are the different sites have been chosen for the most probable the avalanche sites have been identified for these sites. The analysis has been done, and you can see here this is the formation area, this is the middle zone, and this is the runout zone where the deposit will come and deposit here. So you can see here, so using this kind of models, where you have to provide the topography and the snow, the impact characteristics, you can do this kind of modeling. You can tell from where the formation of from where the avalanche will form, where it get deposited. So those kind of analysis you can do. So why earlier I was telling you about the density, because the density measurements across this entire Himalaya are very scarce. So and this model requires the density. You have to provide the density, you have to provide the slope. So those parameters, if you can if you have the SAR data set, using the inversion models, you can estimate the density, slope you can get from the digital elevation model. You can feed those information in these kind of models, and you can do this kind of analysis. Now they have validated their results as well. So it was found that the flow height on the road was around the 5.5 and what they have estimated, what was observed was 5.94. So you can see here, we can simulate this kind of hazards, or the avalanche, and you can see that with the higher accuracy we can do this kind of analysis. So now I'll touch upon some slides on the glacier mapping and monitoring. So you can see here something is moving. So what is it? So it is glacier. So glacier are the mass of ice slowly moving down a gradient. So glaciers normally contains ice, water, snow, and rock, everything debris present over these glaciers. So out of these, ice is the essential component, and glaciers are normally formed due to recrystallization and metamorphism of the naturally fallen snow. So with the time, whenever there is a snowfall, due to the metamorphism, due to the compaction, the recrystallization take place, and the snow becomes ice. And this ice, whenever this mass of the ice becomes heavy, it will move slowly down the gradient. So this is called as glacier, as I shown here, that this is moving like a river. So glaciers are broadly classified as ice sheets and the or the valley glaciers. So these ice sheets are generally present in the Arctic, Antarctic and Greenland. And if you see in our Himalayan region, we have mostly this valley type of glaciers. So there are different types of glaciers. So this is how the typical glacier. So this is the oldest ice, then there is a old ice, then new ice, and then there is a snow with which will become slowly it will become ice due to the compaction. And so this is how the glaciers are formed. So there are different boundaries of the glacier, or we have to identify the glacier in the remote sensing data. We can use the optical remote sensing data. We can generate the fall color composites, and we can map the glaciers. And if there is a debris covered glacier, then we have to go for the thermal remote sensing data as well. So the glaciers have different boundaries. One is accumulation area. In this region, the total accumulation from the winter snowfall is more than the summer ablation, and therefore it is characterized by the snow and gives higher reflectance, and the spectral reflectance is higher in the all three bands. Hence, it appears white on the FCC and can be easily demarcated. So, what I'm trying to tell here, the region where you will have the snow throughout the year, that region is called as the accumulation area. Where is the ablation area? In the ablation area, the total summer melting is more than the winter snow accumulation. So whatever the snow has accumulated during the winter, if it gets melt during the winter, during the summer, the area get exposed is called as the ablation area. So the line dividing between the line between these acclimation and ablation area, it is called as the equilibrium line altitude. So these glaciers will have the moraines along with them. So moraines are normally described as the rock or debris transported by the glaciers. So depending upon these the debris, these moraines are classified as lateral, medial, and the terminal or the end moraine. So I can show here some of the images. So you can see here, this is the lateral moraine, and you can see here there are lateral moraine and the medial moraines as well present on the glacier. So if you see, this is the view of Kedarnath from Chorabari Glacier Lake. You can see here there is a lateral moraine, medieval moraine. If you see entire this Kedarnath shrine, it is located in the medieval moraines. So the glaciers, they have debris cover glaciers also. So glaciers are normally covered by debris in the ablation area. So because of the debris, the albedo of the snow and ice will get reduced. So therefore, extent of the debris cover is important for runoff modeling, and we usually use the SWIR band to map the debris cover glaciers along with the thermal data. So you can see here, this is the Gangotri Glacier. This is the ablation area of the Gangotri Glacier, which is, you can see here, it is mostly the debris covered. So you can see here nicely in this image, these are the lateral moraine, and then you can see the medieval moraine, and then present in the this glacier. So these are the glacier distribution across Himalaya. All of you know that these are called as the water hours or third pole other than the north and south pole. So this is how the glacier, this is the Gangotri Glacier, this is the Satoband Glacier. These glaciers, how they appear in the optical remote sensing data I have shown here. And then you can map these glaciers, how much is the accumulation area, how much is the ablation area. Using the remote sensing data, you can easily map the different regions of the glacier, that is accumulation area and the ablation area. So the gray color shows the ablation area and the blue color shows the accumulation area. And these area of the ablation and accumulation also changes with the time. So you can see here, these are the different companion glaciers of the Gangotri or Gangotri group of glaciers. How much is the ablation area, how much is the accumulation area, and for each glacier, how much is the total area. So if I take the ratio of the accumulation area by the total area, I can get this AAR, accumulation area ratio. So using this, we can also estimate the mass balance of the glacier, how much mass has been left, ice mass has been left in the glacier. So using the remote sensing data, we can also do the glacier retreat analysis. If we have the temporal remote sensing data, and if we can identify the snout or the front of the frontal position of the glacier, we can do the glacier retreat analysis. So in this, we have shown you the how the Gangotri Glacier has retreated between 2010 to 2020. You can see that the glacier front was here in the 2010, which has now shifted to this position in 2020. So this is how the glaciers are retreating, they are losing their mass. And then another study we have done for Mirthuning Glacier, which is also in Uttarakhand, in the Chamole district. So we have used different time period data sets of Landsat. As you know that this is the longest optical data series available. So from 1990 to 2015, the analysis have been performed. and in each year we have identified, this is the false color composite. We have identified the frontal position of the glacier, and you can see that these are the NDWI images, and where we can see that from where the river is starting. So that snout we have identified, and we have identified that how much the glacier has retreated with time. You can see here that the glacier has retreated by around, is retreating around by around 27.43 meter per year in 2015. So you can see here where the snout has shifted from which elevation to which elevation. That analysis we can do if we overlap these snout positions on the digital elevation model. So this is the glaciers have, this Mriktring glacier has retreated from 1990 to 2015. These are the position of the snout. So why this retreat is there? We have analyzed the climate data, that is the temperature data and the precipitation data. So we have found that the winter precipitation and even the winter precipitation, it is reducing, winter precipitation is reducing, and the summer temperature is increasing. So what is happening, even we have analyzed that winter temperature is also increasing in this analysis. So what we have, because of this, the glacier is not getting much recharge, or not getting more snow. Because of that, they are retreating. So you can see here the different literature are available where they have analyzed the different glaciers, how much they are, what is the snow, how much is the retreat of these glaciers, at what rate these glaciers are retreating in different time periods. So you can get this information from these references, and you can see at what elevation their snout is present. Those kind of analysis are possible using the remote sensing data. So once we can identify the accumulation area and ablation area, we can do the glacier mass balance. So I told you that if we have this ratio, accumulation area ratio, we can do the glacier mass balance. So we are the same we have done for the this Mriktring glacier for different time period, and using the different equations available for the accumulation area ratio method. So you can see here the almost these two equations are showing the negative mass balance of this glacier. So even using the remote sensing data, we can map the glacier lakes. So I have shown here, this is the Gepang Ghat glacier, which is in Himachal Pradesh, in the Chenab river basin. You can see with time how this glacier lake is changing. In 1984 it was here, and 1920 the glacier area has changed. So with time the glacier area is increasing. So if there are different type of glaciers, so you can see here, this is the Gepang Ghat glacier lake. So how with time the glacier lake has increased, these different colors are shown in the different years. The spread of the lake, how it has changed over the time, it has shown here. So there are different type of glacier lakes. So these are the supraglacial lake, those are present over the glacier. There are erosion lakes, there are the proglacial lakes or the moraine dam glacial lakes, the blocked lakes. So there are different types of the cirque lakes. So these there are different interpretation keys to identify these glaciers. Lakes such as shape, size, pattern, tone, texture, shadow, site, association. So once we can identify these lakes in the image, we can identify their area with the normalized difference water index, where we use green and NIR band, and we can map these glacial lakes, and we can see how the glacial lake area is changing with time, whether this lake is going to be critical or not. Those kind of analysis can be done, and if it is a critical lake, what kind of hazards can occur, those analysis can be done. So this is how I have shown you the satellite examples, images of examples of each of these glacial lakes. So some of them are blocked lakes, some of them are moraine dam lakes, some of them are supraglacial lakes. So this is how we can identify these lakes in the satellite image. And we have done a lot of studies to map the glacial lakes in this northwestern Himalayan region or the entire Himalayan region. So these are the lakes we have identified in the Kosi River basin of Nepal. So you can see how the glacial lake is changing with time. This kind of analysis we have done. So because of the formation of the lakes, what will happen? It will increase. If it is a supraglacial lake, it will increase the melting of the glacier. If it is a moraine dam lake, then it will push the glacier and it will have more melting here, so the glacier will retreat as well due to formation of these lakes. So there are different criteria to identify the critical glacial lakes. So we have used different criteria, and then we have identified using this AHP approach. We have defined different the factors, and then we have mapped these glaciers in the Sikkim area. So you can see that which lake is highly susceptible to the GLOF. Yesterday you had lecture by Mr. Pankaj Dhote, where he has nicely explained you how the GLOF simulation can be done using the remote sensing data inputs. So these red color glacier lakes are the more vulnerable to the GLOF. Yellow color glaciers lakes are medium. They have medium susceptibility, and these green are have low susceptibility to GLOF event. So this is how we can map the glacial lakes. We can categorize them based on their susceptibility towards the GLOF, that is glacial lake outburst flood. So all of you know what is GLOF. Yesterday he has the lecture on GLOF. So GLOF is a catastrophic discharge of water from the glacial lake due to failure or breach of ice or moraine dam glacier, those formed at the end of these lakes. So such type of sudden discharge from ice and moraine dam glacier may cause a huge disaster. So this is called the glacial lake outburst. So if you see the effects of the glacial the GLOF, so why these there is a rapid increase in this kind of floods because of the global warming, and because of the warming the glacial size are increasing, and they are bursting and causing the hazard in the downstream. So if you see the elements in the at risk are livelihood, human beings, cattle, agriculture, infrastructure, road, bridges, and houses. If you see the GLOF which has happened in 1994 in the Bhutan, it has destroyed this Namche Hydel project, which has been the estimated loss of this was around 1.5 million US dollars. So remote sensing can help us in identifying the potential risk or the critical lakes, and we can do the simulations, and we can generate the early warning to reduce these kind of losses using the remote sensing inputs. So this is the field photographs which we have surveyed the Chorabari glacial lake, which burst and caused the Kedarnath havoc in 2013. So in October we got the opportunity to visit this, and we could do the survey so that we can estimate the volume of the lake, how much water was there. So to improve our simulation, we have done this kind of survey, and similarly we have done the GLOF's simulation for the Chubda lake, which is in Bhutan. So if this lake breaches with the depth of 20 meter of water, so this kind of this much area may get inundated, or the people or the agriculture area along this may get submerged. Even you can see there is a airport as well in this area. So this the entire airport will get submerged due to this kind of GLOF event. So similarly we have done the GLOF analysis for the Padam lake. If it breaches, so how the how much area will get affected. So that's kind of analysis we have done. I am sure that Mr. Pankaj might have shown you this kind of analysis. So you can see here this Padam village may get washed away due to this kind of the event if it happens in the Padam lake. So some more slides I would like to take on the different hazards which those can happen in this snow and glacier. So this is the example of the Gangotri glacier. You know that this is the Gangotri glacier and these are the companion glaciers. So this Meru glacier. So due to the debris flow in the year 2020, what has happened in February 2020, there was a sudden release of the debris. There is a debris flow, and it has blocked the river Bhagirathi river channel, which is coming out from the Gomukh of the Gangotri glacier. So you can see here before image before the event and after the event. So this is, you can see here how much debris it has come and it has blocked the Gomukh region. And you can see when earlier the water was flowing from the center, because of the debris deposition, now the river has taken this path. So you can see here with the help of the remote sensing, what we have done, we have generated the digital elevation model of 2 different time period, and we have estimated how much deposition has of the debris has taken place in the this region, and how much erosion has been taken in the Meru river Meru glacier. So there was around 8 to the power 10 to power 6 meter cube or million cube, 8 million cubic meter of material has been eroded, and around which is deposited over the 0.25 kilometer square area in the downstream in this which has blocked the this Gomukh region. So this study we have done, it has been published in Geomorphology journal. Another event has taken place recently in Uttarakhand on 7th February 2021. So here what has happened, this rock slide triggered the flood in this Rishiganga and Dhaulaganga river basin. So this rock, it has been estimated is that there was 20 million cubic meter volume which contains raw deposited ice, snow, and it got detached from the northern slope of the Trishuli mountain. So from this region it got detached and fall over the this river channel. So what has happened because of this, the channel the there was a huge discharge in the channel which has destroyed many of the hydropower projects, and because of the deposit the lake has also formed in this region. So how you can see here, this is the planet scope image of same day. You can see here after the event, you can see here there are some bright white pixels. So these are showing the dust plumes because of this event. Because of this event, you can see here along this the channel, you can see the dust plumes. So you can easily identify these kind of dust plumes in this image. So then later on we have done further analysis. We visited this site. You can see here this is the region from where the this rock has fallen, and we can see that this is the pre-event. You can see here nicely this there is a hanging glacier, and which has been removed after the event. So you can see this kind of analysis has been done, how much based with the help of the field photographs, the volume of this rock or the rock glacier has been estimated, and we have estimated if this kind of rock will fall from certain height, how much damage it can cause in the downstream. So these were the examples of the optical remote sensing data in the glacier studies. Now I'll take upon some slides on the SAR data for the glacier studies. So you can see here, see glaciers in the monsoon, you will have the cloud present over it, so you may not be able to map the glaciers. In the winter you will have the snow, so you will not be able to identify the boundary of the glacier. So if you have the SAR data, you can easily map the glacier even in the monsoon when you have the rainfall, and when in the winters when you have the snow cover present over in the region. So with the help of the SAR data, If you have the temporal SAR data, you can also identify the different glacier zones, such as percolation zone, upper percolation zone, middle percolation zone, the bare ice, and the debris covered glacier. So if we have the temporal active remote sensing data, SAR data of different seasons, early summer, late summer, and the winter, because of the condition of the slope, the backscatter will change. So based on if we do the backscattering analysis, and if we can generate the composite of different time period, we will get this kind of output. So this is the composite of different time period SAR data of different dates and different seasons. So early summer, late summer, winter, if I generate a recomposite, I'll get this kind of output. So these colors or these tones represent different glacier zones. So the purple color, it is mainly the middle percolation zone. This the pinkish pink color tone is the middle percolation zone. This purple color is showing your the wet snow zone. And because this glacier is mostly the debris covered, so this greenish tone is coming because of the presence of the debris in the region. So if we use simple classification techniques, we can generate the boundaries of the different zones, that is percolation zone, middle percolation zone, wet snow zone, dry snow, bare ice zone, debris covered glacier. So we know that the boundary of the lower percolation zone and the bare ice is called is the representation of the your equilibrium line. So the line on the area below this is your ablation area, and the area above that is your accumulation area. So you can see here, this is the accumulation area of this glacier, and this the orange color is your ablation area of this glacier. So the SAR data, it overcomes the limitations of the optical remote sensing data, because if you want to do the glacier mapping, and you want to map the accumulation area and the ablation area, so we prefer the optical data of your end of ablation time period. So this time period falls in the end of August or early September in India. So during this time, as there is a monsoon season, so you may not get the cloud-free data. So in absence of the cloud-free optical data, the SAR approach we may be very useful to delineate the accumulation area and the ablation area. And with the help of this composite approach, where we can identify different glacier zones, we can improve the estimation of ELA. And once if we have the highly accurate ELA, our glacier mass balance analysis will improve. So this is what we have achieved in this analysis, which we have published in the Journal of Indian Society of Remote Sensing. Then you can see some more example I have shown here for Siachen Glacier. You can see here the composite of different time period. So this is the images of different time period, and this is the composite, and we could generate this kind of glacier radar zones. So you can see here this is the high percolation zone, this is middle percolation zone, the green color shows the bare ice zone, and the yellow color shows the debris covered ice. So you can see here, with the help of this kind of analysis, we can easily identify the ELA of the glacier, and we can do the glacier mass balance. So similarly, we have done for the glaciers present in the Arctic region, Svalbard. This is the Monocobin glacier. This is the SAR composite, and we can generate this kind of glacier radar zone or glacier phases map using the SAR data sets. Even we can estimate the glacier velocity with the help of the SAR data. So there are different methods. You can use the interferometric SAR approach to generate the to estimate the glacier velocity. So this is the 2 time period images we have taken between the 2 period. How much is the coherence we have estimated? Then what is the phase change, and then we have estimated we have derived the interferograms, and based on these interferogram, the displacement in the line of sight has been estimated. Once we have the displacement in the line of sight, we can convert that into the glacier velocity. So for Siachen Glacier, we have estimated the glacier velocity. For Bada Shikri, this is the spatial map of the glacier velocity, and this is the velocity of map of the Gangotri Glacier. So you can see here the maximum velocity is the order of around 42 meter per year in the Gangotri Glacier. It is 32.5 meter per year for the Bada Shikri Glacier, and it is 135 something meter per year for the Siachen Glacier. So you can see the Siachen, it has more area under the higher altitude region, so thereby the velocity is higher in the Siachen Glacier. So if I draw this along the trunk, if I draw the line and I retrieve the velocity, so you can see here how the elevation is changing along the glacier and glacier trunk, and how much the glacier velocity is changing with time along the glacier. Sorry. So you can, this kind of analysis can be done using the remote sensing data. So another approach is this approach, the interferometric approach is suitable for the slow moving glaciers, because if it is a slow moving glacier, you will get some coherence between the two time period. So such as Sentinel SAR data, you know that the temporal time period is 12 days. If you have both Sentinel 1 and 1B pass over your glacier, for your temporal resolution will reduce. So it may reduce to 6 days. So if you are getting some coherence within 6 days, so you can do the analysis, and you can retrieve the glacier's surface velocity. If the velocity is higher and you may lose the coherence, so it is suggested that you should go for offset tracking method. So what we do, we have two different time period images, and we give this search window, and within the search window it identifies the features, and within two time period, how the feature has moved from one place to another place. Based on that, it estimates the velocity of the glacier. So this is the example of glacier velocity estimated for the Monocobrim Glacier, which is in Arctic, Svalbard Arctic. So for different time period, so in the 2015, 16, 17 and 18 and 19, so you can see the glacier velocity, it is changing, and it is increasing in the year from 17, 18 and 19. So what we have seen that there is a surge of the glacier. It is a surging glacier, and it terminates in the sea directly. So that is why if you see in the trunk of the glacier, we have more velocity in this glacier. So you can retrieve in the different season of the year how the glacier velocity has changed. So you can see that is more or less stable in the winter or in these years, and when the surge has initiated, the glacier velocity is increasing. So this kind of analysis can be done using remote sensing data. Even you can map the crevices. So you can you know that the crevices are the cracks in the surface of the glacier, those caused by the extensive stresses within the ice. So these stresses may be generated because of different at the different location because of the different processes. So you can also map the crevices in the satellite images, and you can do the analysis of those. So this is the optical remote sensing data, and this is the Sentinel-2 data of this the frontal position of the Monocobrim Glacier. You can see these are the crevices. As I told you, this is the sea terminating glacier. And during this time period, the surge has also occurred. So there are different stresses in generated, and those have induce this formation of the crevices. So because of these crevices, these get the ice get detached from the glacier and gets deposited in the sea. So similarly, you can identify the different crevices on the cartosat images. I have shown you some examples. So in conclusion, I would like to say that the remote sensing plays critical role in mapping and monitoring snow cover area. Microwave remote sensing data is very useful in retrieving the snow physical parameters. Snow cover area and its physical parameters are important for avalanche studies. Glaciers, as you know, there are the water towers. So the glaciers can also be mapped and monitored using remote sensing data, either optical, microwave remote sensing data. Both data sets can be used. Glacier lakes we can map and monitor using the remote sensing data. And the glacier dynamics, such as the glacier velocity. If you can estimate the glacier velocity nowadays, you can also estimate the glacier ice thickness with the help of the glacier velocity. So this is all from my side, and thank you so much. If we will break for 5 minutes, and then we will have the some whatever queries you have, we will discuss them. So thank you so much.